I think we can start. Okay. Hello, everyone. Hello, Onur again. So thank you for accepting this invitation. So it's a pleasure for us to hear you today about, you will talk about memory-centric computing. So a brief introduction. So Onur is a professor at ETH in Zurich in Switzerland, and he's a famous researcher in the computer architecture domain. And I think that most of you already know Onur work at least. And yes, it's a real pleasure for me, and I think for the community to hear about you today. So you have the floor, no? So one question. So can I record the presentation, the talk?
Yes, yes, absolutely. You can record, and
okay.
I'm happy to get a copy afterwards also.
Okay. And also, do you want questions during the presentation, the talk, or at the end?
Sure. Any time is fine, actually. I have a lot of I have a lot of slides. People can interrupt me, ask questions, and we can discuss.
Okay, good. So you can ask your question in the chat, or you can just turn on your mic and ask the question. And okay, so I will share the session with Caroline. So Caroline, feel free to if you see a question in the chat, you can interrupt and ask the question.
I will.
Thank you. You have the floor, Onur.
Okay, thank you. Yes, I don't see the chat, so please interrupt me if you have some questions. Okay, thank you, Alan, for inviting me. I'm going to talk about memory-centric computing. As I said, this is a topic that we and others have been working on a lot, especially in recent years, I would say past 10 years or so. And there's a lot happening in this domain. I have a lot of slides. I don't need to cover all of them, but I'll give you a general overview of what's happening in the field. I will start with motivation, of course, to begin with, and we will take some time. And the main issue with many computing systems that we design today is they're really bottlenecked by data. And data is really important for many workloads. Important workloads are all data intensive. They require rapid and efficient processing of very large amounts of data. And on top of this, data is increasing. We can generate more data than we can process in many domains today. And we're doing increasingly sophisticated things on the data that we're generating. For example, neural networks have clearly been successful recently because of the ability to generate and train using large amounts of data, using GPUs especially. And you can see this talk was given by Cerebras' chief architect, Sean Lee, in one of our seminars. And he shows over here the memory requirements of neural networks, as well as the total training computation requirement. And both of them are growing exponentially, as you can see. But neural networks are not the only application. There are many, many important applications that we're dealing with that are also quite data intensive. These are some examples over here. And data is a huge performance and energy bottleneck. And also on the mobile end, we are generating a lot of data, especially in IoT sensor devices, for example, but also on our cell phones. And data is really bottlenecking the performance and energy of our devices. I will briefly talk about emerging applications like genomics. We're doing a lot of work in this area. And this is another area where we can generate a lot more data than we can process today. You can see that people have been sequencing genomes. Recent COVID-19 outbreak and pandemic has actually enabled people to sequence COVID-19 genomes and variants very quickly due to the developments in the sequencing technology. And the reason we can generate a lot of data in many domains is because of the cost of generating the data has been reducing significantly. In case of genome sequencing, you can see that with the introduction of high throughput sequencing technologies, the cost of sequencing a genome has dropped dramatically. Compared to Moore's law over here, the transistor cost has not been dropping as much, as you can see. And more recently, with the introduction of nanopore sequencing technologies, the costs have been dropping significantly. As a result, we can actually generate a lot of data using our sequencing machines, which are not perfect, but they're very good at generating data. But now the bottleneck shifts to moving that data to the machines that analyze the data, as well as analyzing that data so that we can do scientific discoveries, as well as improve personalized medicine, improve decision-making in medicine in general. But essentially, we're bottlenecked by data. And clearly, genome analysis can have many use cases and applications. I'm not going to go through this in detail. I will refer you to some papers and talks. But I believe these applications are especially limited by the way we're designing computing systems today. Basically, we're kind of blocking what may come into the future because our analysis is extremely slow. So let me give you an example of a data generator in the genomics domain. This is the nanopore sequencing device. It's an old one, but you can see that it's very small. It's very capable of sequencing someone's genome. It's relatively fast. Unfortunately, it has no processing capability. So if you want to analyze what comes out of this, you have to move the data, usually to a substantial computer, the data center potentially. Imagine actually data is being generated by many of these devices all over the world. And that data movement takes a lot of time, clearly. And you have to do sophisticated things on the data. So basically, this is a very nice device for data generation, but a terrible device for data analysis. And this is really the problem we're having today. As a result, we have to move the data a lot, and it becomes a performance energy bottleneck. And this picture kind of summarizes the problem we're having in genome analysis. But in general analysis today, we have very special purpose machines for generating data, genomic data in this particular case. And then we use general purpose machines for data analysis. There are two major issues. We move the data across the world, let's say, in a macro scale, as well as in a micro scale inside the general purpose machine a lot. And then we have slow and inefficient processing capability because our machines are not specialized for genome analysis. And this picture is really similar for many data generators and analyzers today. Remove the picture on the left, replace it with many video cameras, for example, and then you have the same problem at hand. Replace it with many clicks that are generating over the internet, you have the same problem. Basically, today we're great at generating data, but not at analyzing it. We have a lot of works in this domain. I'm going to mention some of them later in this talk, but if you're interested in genome analysis, I believe there's a huge world of opportunity over here in terms of system design for genomics. And you can see some of these papers, and there's a beginner reading that we were recently invited to write in a journal, as you can see. I will briefly mention one thing that we have done to accelerate genomics, but also weather modeling using FPGAs. I believe FPGAs are actually quite interesting, and we've been doing a lot of work on them, especially with near memory acceleration. Here in this particular work, we have used a high bandwidth memory-based FPGA board where you can specialize the FPGA logic for the application and have very high bandwidth access from that logic to the main memory. And then you can offload weather modeling as well as genome analysis computation to that very specialized logic. And we actually did a lot of design space evaluation over here. I'm not going to talk about the details of it. Clearly, this requires a lot of programming effort to make sure that you offload the right portions of an application to the FPGA. But the results are very promising. And these are real systems today that you can buy and you can optimize. Basically, even today, if you actually do this sort of specialization and near memory computation, you get significant performance improvements. You can see 5 to 27x compared to a general purpose machine. And you get significant energy efficiency improvements at the same time. And I will refer you to the paper for more detail. We're going to discuss more near memory computing approaches later on. But this is today, basically. Today we can do this. My talk is mainly going to be focused on future. What else can we do in the future that can actually unleash even more benefits in terms of performance and energy? And ideally, we would like to improve both performance and energy. We don't want to have a trade-off, improve performance that degrades our energy. We don't want that going into the future, and I will motivate that as well. Okay, so there's a lot more work that happens in genomics in terms of hardware, software, co-design, and acceleration. I will not have time to go through them. I will talk about in-storage genome filtering, which was published in ASPLOS this year, later on in the talk again. But there are a lot of interesting applications like graph genomes, graph analytics, and base calling, which I don't have time to go over. But again, as I said, if you're interested, you can read some of these papers. You can also watch some of these talks. This was a more recent talk that I delivered at the Systems for Post-Moore Architectures workshop at Eurosys, and you can find online as well. And there are more lectures. Okay, I think this was a forward-looking application. I could actually talk a lot about applications, but we don't have time for it. But essentially, this sort of applications really overwhelm modern machines today. They overwhelm the storage and memory capability, communication capability, as well as, and in the end, the computation capability that we have in our machines. They also greatly impact robustness, energy, performance, and cost. We will talk a lot about all of these very soon. But if you go back to the fundamentals, fundamentally, a computing system consists of 3 key components: computation, communication, and storage/memory. And if you actually take a broad view of what has happened in the computing system design over the last 80, 90 years, we've heavily optimized the computing unit It's really the king of everything else. And we've kind of ignored the communication and memory and storage units. Relatively, of course, right? Clearly, people are working on communication and memory and storage, but in a very different way than we think about computing units. Communication and memory and storage are not thought of active components. They're basically thought of as things that serve the computing unit with data, and interesting things happen in the computing unit to the data, like computation. And this is an example of processor-centric design that we have. This is a cartoonish picture that I drew a bunch of years ago. If this is a multi-core system, you can see that cores are very small. Computation units are a very small part of the system. Most of the system is really caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, main memory, other interconnects, storage, other interconnects. Basically, most of the system is really dedicated to storing and moving data. And if you do the calculations, more than 95% of the area of a single node is dedicated to storing and moving data. Unfortunately, the system is still bottlenecked by memory, as I will show you later on. Basically, this picture should tell us that maybe we're doing something wrong in the design of our systems. We're dedicating most of our resources to store and move data, yet we're still bottlenecked by data. And if you don't believe my picture, this is a picture from AMD, a recent processor. You can see that the part that I kind of boxed over here, the green part, essentially is L3 and L2 caches. There's global memory interconnect. Basically, most of the chip is really for moving and storing data. And AMD is adding even more caches. This is not just AMD, but essentially the computing industry. Because we're in this processor-centric paradigm, we cannot get out of easily, at least currently. We keep adding more and more caches. And these caches are actually terribly utilized. Most of the data inside the caches are not very well utilized. And you can see that there's 3D stacking technology to increase the cache sizes. This is IBM's Power 10. You can see that most of the chip is still data storage and movement. And here I circle the L3 and L2 caches, but then there's a huge memory signaling interface, interconnect interface, PCIe interface. All of these are related to data storage and movement. This is Apple's M1 Ultra system. You can see that the chip is really mostly SRAM, and then there's huge amounts of memory. And then in the darkness lies storage, which is essentially most of the system, as you can see. So the question I will ask in this talk is this really the right way of designing systems going into the future? And again, even though we do this, data overwhelms our modern machines. So these are applications that we've examined together with Google. Very interesting applications, clearly. We're exercising a lot of them today. I'm using Chrome to connect to this call, for example. Somebody is probably analyzing our data using some machine learning inference engines, and we're clearly using video codecs right now in this call. And we've analyzed these applications, and we found that more than 60% of the total system energy is spent on data movement in a real system. And I believe this number is actually underestimated because we used relatively comparatively small data sets as to what we are seeing, for example, in neural networks, genomics, etc. So this number can easily go up to 90–95% in some of the applications that we see. Okay, so going forward, my axiom will be that we need to design intelligent architectures because we're going to bet our lives on them, for example, in self-driving cars. We should perhaps handle data well. So the question, of course, becomes, how do we handle data well? I believe there are 3 components to it. I'm going to especially focus on the first one, but I will give you an example of the second and third one as well. I believe we need to look at it holistically so that we actually handle data well in the entire system. So the first one is we should ensure that data does not overwhelm the components. And this requires intelligent algorithms that reduce the amount of data, intelligent architectures and system designs that minimize the data movement, and in the end, co-design of algorithms, architectures, and devices, the entire system stack, I believe. And I will talk a lot about that, as I said. But we also should design our systems to not make, let's say, not intelligent decisions, meaning we should take advantage of vast amounts of data and metadata flowing through the system so that we can improve the decision-making that happens in the system architecturally and at the system level. I'll give an example. I have a memory controller in this phone, which is about 4 or 5 years old, let's say. And this memory controller has seen a lot of data flowing through it, yet it has learned nothing out of it. Basically, the decisions it makes at the memory level doesn't consider what has happened in the past. It basically looks at the structural properties of DRAM and the request types, and basically says, okay, if this row buffer is open, I'm going to schedule this request earlier than this other request. Very simple heuristic-based decisions that are dictated by humans. This is very different from an experience-driven, data-driven learning machine. So I believe we need to change the way we design controllers in our system, both in hardware as well as software and cooperatively, so that a memory controller, for example, learns what is important and what is not important, what decision should be taken in the future so that you can maximize the performance or energy, etc. And this requires learning and experience-driven learning. In particular, we've been looking at reinforcement learning-driven memory controllers, as well as prefetchers, for example, and also storage system designs. I believe we need to do more and more of that going into the future. And the third component over here is we should really understand and exploit properties of different data, because data has many, many different properties. It has many different characteristics. Today, we do not really expose them to the system, especially in general purpose systems, but this is true also for specialized systems to a lesser extent, but even in specialized systems, we don't expose a lot of characteristics of data. But if you look at data, it clearly has performance characteristics, locality characteristics, parallelism characteristics, privacy characteristics, security characteristics. It has approximability characteristics, error tolerance characteristics, many, many other characteristics, compressibility characteristics. And we don't expose this or even discover these at the software level. If we actually expose these semantic characteristics to the architecture and the system designs, we can improve the data management algorithms. Again, I'll give an example from the memory controller. Today, memory controller gets 2 requests. 2 requests have no semantic information associated from the perspective of the memory controller. Memory controller says, okay, I'm going to prioritize this request over the other one because I think it's going to take faster in memory. But is that the right decision? Maybe this request that you're delaying is a security critical data, and maybe somebody can time that request and actually create a side channel attack. So if we actually were able to label the data semantically, we would service a security critical data much differently compared to a security non-critical data, for example. This is just one example. There are many, many examples about. So basically, I think corollaries of these 3 different things lead us to more data-centric designs as opposed to processor-centric designs, which I will focus on. More data-driven designs as opposed to designs that make designer-dictated, human-dictated decisions. And then more data-aware or data characteristic-aware designs compared to component-based myopic decision-making designs. As I said, I'm not going to talk about the data-driven and data-aware parts, but you can find that in our talks, and I will mention them later on. But I believe if you look at all of this that we have discussed, we really need to revisit the entire stack to make an architecture data-aware, data-driven, as well as data-centric. And I will give you examples from the data-centric portion today. I believe we can get there step by step, so the task is not overnight overhauling everything. It's like we will evolve to that over time, hopefully. And if you're interested in this vision, we have recently written papers about it. This is a short one. You can look at. Okay, so let me jump into data-centric or memory-centric architectures. And once you jump into this, you will see that there's a lot that needs to go on over here also. If you want to list the properties of a data-centric architecture, we will discuss especially the first one. We want to value data so that we don't move the data because that's expensive. We want to process the data where it resides or where it's generated, where it makes sense essentially. So this leads us to the topic of this talk. But we also want low latency and low energy data access. Processing data where it resides actually gets us somewhere there. But fundamentally, reducing the device latency and device energy is also very important, also interconnect energy. And that's, I'm not going to talk about that, but there's a lot of work that's going on in this area as well. Clearly, we want low-cost data storage and processing. There's a lot of interesting work over here as well. And we want intelligent data management, intelligent controllers handling robustness, security, cost, performance. I'm going to talk about that one especially because that's going to motivate the first one as well. Okay, so let's jump into processing data where it resides. I also call processing data where it makes sense. Basically, today we have no option. We have to move the data to processing elements, which are CPUs, GPUs, FPGAs, some accelerators, but they're all far away from the data storage engines. Why should we not actually put intelligence into our data storage engines like DRAM, storage units, sensors, so that processing is distributed across the entire system and CPU doesn't become a bottleneck because that's the only place where you can do the processing. Like I say CPU, but you can imagine accelerators are very similar, right? So today, computation units are very compute-centric. This is not a new idea. Clearly, people have thought about it. There are very smart people who actually wrote papers in the 1960s. This is one example. I would recommend people to look at it. And if you find older papers, please let me know. And Harold Stone, who has a beautiful textbook on computer architecture, also worked on it in the 1960s. Now, what is different today? Why didn't it pan out until, let's say, recently? And it still needs to be proven, basically. Basically, today, the conditions we're in is very different. We are having huge problems with memory technology. And we have a huge demand from application systems because we have been extremely successful in improving the computation capability of our systems, thanks to Moore's law and also architectural improvements. And our designs are kind of squeezed in the middle. The technology is not going well because we have a lot of issues in technology scaling. I will briefly talk about RowHammer, for example, but there are a bunch of issues as I will discuss. And many of these scaling issues demand intelligence on the memory side so that we can have some computation on the memory side to fix the issues. On the application and system side, we have a huge data access bottleneck. We have huge energy and power bottlenecks, and also more increasingly sustainability bottlenecks. And data movement energy is dominating computation energy. And at the same time, we need performance, energy, sustainability. We don't want a trade-off between them. So essentially, we're kind of squeezed in the middle. Technology is pushing us, and applications are pulling us. We're kind of, we need to do something else. So let's talk about the technology issues first. But before I jump into it, I will say that if I showed you the processing in memory landscape about 3 years ago, you would not have seen a lot of these that I'm going to show you. So 3D stack memory technologies are actually good enablers. We will talk about them. We have a logic layer underneath many memory layers, and you have high bandwidth, low latency, low energy connections in the logic layer, and you can implement specialized logic as well as CPUs in the logic layer. We're going to discuss that. Micron has been experimenting with automata processing, but more recently, Opmem company, which is based in Grenoble actually, has introduced a more general purpose processing in DRAM engine. I will talk about that also. And even more recently, Samsung, SK Hynix, and Samsung and Alibaba have introduced processing inside DRAM as well as processing on the memory module type of chips, as you can see over here. We will briefly cover them later on, but basically today industry is actually picking up these issues. Actually, I have not even talked about some other things over here because there are many other experimental chips and startups as well in industry, as well as in big players. So we will get back to this. Today, essentially something is happening. So why is it happening? Let's go over the push from technology relatively quickly. I'll not spend a lot of time on this, but it's important to cover because this is going to hurt us even more into the future. Basically, today we are having a lot of issues with DRAM technology scaling. As a result, industry is very open to new memory architectures, and they want controllers close to DRAM. This was not the case about 10, 15 years ago. And if you're interested, we have written papers about it, but this is an early paper where we discussed that memory scaling issues are going to be real, and we should do something about it, have a systems and architectural perspective to fix the issues. So this is one example data that we've gathered together with Facebook about 8 years ago. Actually, the research took about 2 years, so more than 8 years ago, as you can see. But we analyzed all of the errors that we see in the data centers, production data centers, while the applications are running. And you can actually see a correlation, very strong correlation between the DRAM chip density that's employed in the servers and the relative server failure rates. Very strong correlation. If the chip density is larger, meaning the capacity of the DRAM chip is higher, you get much more errors in the servers. And this clearly has very many system level implications. What is the reason? Because essentially denser chips mean smaller cells and cells that are closer to each other. And you get a lot more noise, a lot more errors in such chips. As a result, you get more errors exposed to the memory controller as well as the software. And we talk a lot about how to fix these issues like page offlining, etc., its effectiveness. You can read the DSN paper that we wrote in 2015. I'm not going to go into it, but this is real evidence from the field that DRAM chips are affecting the operation of our data centers. And then we also wanted to actually do more small-scale studies to really understand the behavior of these errors in real DRAM chips. And we built FPGA-based infrastructures that look like this. And we did a lot of experiments, and these are more recent examples of our infrastructures. If you're interested, we've actually released a more recent one. I don't have the link here, but our original one was called SoftMC. We recently released a DDR4 version called DRAM Bender. If you're interested, you can check it out. And we did a lot of studies, and we have, together with Intel, we have found out that you can actually predictably induce errors in most DRAM memory chips. This is known as the DRAM RowHammer phenomenon. Some of you may have heard of it. And the issue is that you disturb cells, you corrupt data in memory by having a specific access pattern. And the specific access pattern looks like this. Essentially, memory consists of rows, and you can actually read data from a row by applying high voltage to it. And then if you want to read some other row, you apply low voltage to it. In DRAM, this is called activate precharge. And by doing simple loads and stores, just loads actually, you can activate a row and close a row. Now, if you keep doing this repeatedly, activate precharge, activate precharge, activate precharge, activate precharge, with many loads, you can do this from a user level program as well. It turns out, if you do it enough times before the cell gets refreshed, some vulnerable cells in physically adjacent rows get corrupt. Clearly, this should not be happening. By just reading from memory, you should not be changing anything at all, let alone rows that belong to potentially some other applications. And some of them may be extremely security critical or privacy critical. So this is an example of a scaling problem that's actually very dangerous, let's say. We call this the hammered row, and we call this the victim rows. And essentially, we showed that more than 80% of the DRAM chips, recent DRAM chips at the time, from all three major manufacturers, there are only three major manufacturers in DRAM in the world, are vulnerable to this effect. Our more recent results show that actually all of the chips from all manufacturers are actually vulnerable because technology scaling has improved in the sense that cells are becoming smaller and closer to each other. As a result, these sort of disturbance, noise effects are becoming much worse, and RowHammer is becoming much worse in the field. And people have actually picked up on this, and they basically show that this is a huge system security vulnerability. And you can see that some folks are writing articles, forget software, now hackers are exploiting physics. And that's actually a real good high-level description of what's happening here. Because of physical issues we're having at the memory technology layer, hackers can actually exploit those bit flips that are created systematically and actually take over your system or leak private data. And there are many sorts of attacks that were shown. Okay, I'm not going to talk a lot about RowHammer. That's a completely different talk. We can talk about it for hours, but I will leave you with some talks that you can watch if you're interested. And if you don't have a lot of time, this is a talk that we delivered for just 20 minutes summary of RowHammer recently at ASPLOS also. And if you're interested, there are papers on it clearly that show that RowHammer is real, and there are many other scaling issues that we need to worry about. And this is a more recent paper that we were invited to write that summarized the field in 8 pages. Okay, so that's one scaling issue, but there are other scaling issues also. So this is an example of a hybrid memory. If memory technology is not scaling, if one memory technology is not scaling very well, why not add other memory technologies to the system or other types of the same memory technology? So different types of DRAM, for example. This is already happening in GPUs, for example, or different types of memory like DRAM and phase change memory. And the idea over here is to put together different types of memories and design the hardware and software cooperatively so that we can achieve the greens of each technology as much as possible, while avoiding the reds of each technology as much as possible. And clearly, this requires a system-level approach. This requires intelligence in the memory controller. This also requires potential intelligence in the system and the software. But I'm not going to go into it. There's a lot of work clearly that's going on in this area. So my point is, to solve this sort of scaling issues, you need intelligent controllers. In fact, for RowHammer, we have been designing intelligent controllers, and industry has been designing intelligent controllers as well. And this intelligence is going to increase and increase so that we can ensure that systems are free of RowHammer, which they're not currently. Okay, so industry is also writing papers about it. It's not just us. Clearly, there's work in academia going on, but this is a paper from Samsung and Intel, two companies that don't normally talk to each other without heavy lawyer protection, let's say. And these folks have come together and wrote a paper in 2014 saying that we're having a lot of difficulty with memory technology scaling. We should have intelligence in the memory controllers to actually solve some of these problems. And again, there's a lot of things that you can do with intelligent controllers that I don't have time to go over. And this sort of system actually already exists. If you look at our SSDs are successful because we have intelligent controllers that make our SSDs work. Otherwise, the flash memory technology is actually very unreliable. But an intelligent memory controller goes and does a lot of computation to make sure that, and also signal processing, to make sure that the data that we're getting from flash is actually reliable. And if you're interested there, we also do a lot of work in SSDs and flash memory. And this is a paper that we have written where we summarize the advances in flash memory controllers. Okay, you say maybe, okay, that's DRAM and flash, that's old stuff. Why not look at new stuff like emerging memory technologies? Those are clearly interesting. There needs to be heavy investment for this to make it happen. In fact, Intel has recently decided that they've invested too much and it's going to become even worse for them to invest. So they reduced the investment in this direction, which is unfortunate. I believe people should be examining emerging technologies. Unfortunately, emerging technologies, we have also been working in this area. Emerging technologies all have problems. They also need intelligent controls. For example, something like phase change memory has so many endurance issues, so many noise and error issues that you need to have an intelligent, wear out issues that you need to have an intelligent controller to make it work. So basically, we cannot escape unless we come up with a fundamentally better memory technology, which is not in the horizon of anyone currently. We cannot escape from the fact that technology scaling is going to hurt us, and we need some intelligence on the memory side to actually fix these issues. Okay, I think I've harped on this takeaway a little bit. We need intelligent controllers to avoid many failures and enable better scaling in the system. So that was the push from technology. If there are any questions in this topic, I can quickly take it now, or I can keep going. I'll maybe pause for a second over here to give you an opportunity to ask questions related to this part.
Questions? Will you talk about the performance overhead of this approach, intelligent in the, if you put intelligence in the controller, memory controller?
Oh, okay, yeah, very good. I don't have time to talk about it, but essentially, yes, there will be some performance overhead because the memory controller, for example, is trying to prevent a RowHammer attack, right? And we've actually characterized in our works, you can, if the number of activations that you do, that you need to induce a bit flip is very, very low, that performance overhead increases. So at some point, the technology scaling becomes so worse that that performance overhead can be 20% or 80% or even 100% in some cases. So basically, we need to have much more efficient solutions to solve these problems as technology scaling becomes worse and worse. Today, the performance overhead is not that much, but it comes with an area overhead. So you can actually turn the performance problem into a hardware area problem, which also consumes energy. So actually, energy gets impacted, unfortunately. Okay, then I will move on. Again, feel free to ask questions anytime. So let me now switch gears to the other end. We've been talking about the lower technology issues. Now I'm going to talk about the systems and application issues at the top, let's say. And here we have a lot of issues. As I said, data access is a major bottleneck, energy consumption is a key limiter, and data movement energy dominates computation energy. I'm going to give you examples from all of this. But before we go into it more, I think the bigger question, we have a bigger responsibility to the world in this case, where we're professionals designing computing systems or researching computing systems. Do we want to have computing systems that lead to a world like this, or do we want to have computing systems that expend so much energy and create so much sustainability issues that in the end they will contribute to a world like this? I would choose the first one, I would say. So we want to be energy efficient, we want to be sustainable, but we also want to not give up high performance. We want all at the same time, essentially. And the question is, are we designing our systems right for all of these at the same time? And my answer is no, basically. Today, we have a huge problem, and our current design principles cause great energy waste, even though data access is the major performance energy bottleneck. Essentially, we're moving data all around, as I said earlier. As a result, we're causing great energy waste. We also have a lot of performance problems because we are moving data all around in our system at the macro scale as well as the micro scale in a single node. So we also get great performance loss. I put it in parentheses because in some applications we don't get this performance loss, especially when our mechanisms work right. So we actually complicate our systems to overcome the performance loss. What do? We add heavy layers of multi-threading. We add many layers of caching, prefetching, out-of-order execution, and all of these really complicate the system. And this complexity leads to even more energy waste, especially when it doesn't work. So we're in a vicious cycle, basically. In many applications, it doesn't work very well. The caches are not utilized well, prefetching is not easy, multi-threading may not be possible, and auto-order execution may be extremely costly and doesn't provide a whole lot of benefits, especially random access applications, for example. The cache hierarchy doesn't work right. So we're in this vicious cycle where we're compounding our energy waste. And to get rid of any vicious cycle, we really need to realize where the problem lies. And I think the fundamental problem is we're processing data far away from the data. And if you go back to this picture, we're basically heavily optimized the computing unit. We're very processor-centric. All data gets processed in the processor at great system-level cost. And we will see that system-level cost in a little bit. And we know actually the system-level cost is great. So this is a quote from Dick Seitz, who was the chief architect of alpha processors in 1990s, which were the fastest processors of their time. And he basically wrote this one-page article after they designed one of the alpha processors, one of the flagship alpha processors. He basically says that it's all about the memory. Basically, he says that we've designed this architecture to complete 4 instructions every clock cycle. Unfortunately, on this important database workload, it's finishing 1 instruction every 4.7 clock cycles. So it's operating at less than 5% of its peak bandwidth, peak computation bandwidth. Why? Because it's waiting for data to come back from memory. And he finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward about 10 years. This is data from my own PhD thesis, and we did a similar study with Intel, with using all of the applications that they use to design their processors, and we found out essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. This is a flagship Intel processor, and you can read in our paper the full data if you're interested. Fast forward about 10 years, this is data from Google. Google, in their data centers, they analyzed all of their workloads according to them. And in this beautiful paper in ISCA 2015, they show that most of the time, the flagship Intel processor, again, flagship processor of its time, is waiting for data to come back from memory. It's doing useful work only 10 to 20% of the cycles. Okay, so this is essentially the bottleneck we're facing. We have a grossly imbalanced system. Because processing is done on only one place, data moves a lot, and this is clearly low performance, and we're wasting a lot of resources. This is also complex, and I will show you that it's very energy inefficient. Even though we have an overly complex and bloated processor, and also accelerators currently, to tolerate data access from memory, this leads to energy inefficiency, low performance, and complexity. And this is the picture that I showed you earlier. Even though we dedicate most of the system to store and move data, the system is still bottlenecked by memory, as these results clearly show. Let's take a look at the energy perspective. Energy perspective is even worse than performance perspective. This is data from Bill Daly's high-peak keynote presentation, 2015. This data is relatively old, but the major trends are the same. So a complicated arithmetic operation today is very cheap in terms of energy, 20 picojoules. A DRAM read or write is 16 nanojoules, very expensive. So the difference is 800x over here. Today, it's somewhere between 2 to 3 orders of magnitude. Basically, a memory access consumes 2 to 3 orders of magnitude the energy of a complex addition. Now, the question, given this, the question we should ask ourselves is, if you're doing an addition operation, it has 2 operands, and it has 1 result. Does it make sense to bring those 2 operands with 2 different DRAM reads into the processor, and then write back the result to potentially some other memory location with 1 more DRAM access? So that's 3 DRAM accesses to do a complicated, but very cheap in terms of energy, arithmetic operation. To be able to overcome the energy cost of those DRAM reads or writes, you really need to be able to reuse the data more than 1,000 times. And actually, you can do the calculations over here if you're interested. But our caches are not that effective today, especially in the workloads that we're looking at. There are many workloads that are more or less random access, and they're really overwhelming the memory hierarchy. Okay, so that was a complicated arithmetic operation. If you compare a memory access to a cheaper arithmetic operation like a simple integer add, 32 bits, it's actually much worse. So the energy is really 6400x. Now, if you actually change that to 4-bit integer add, it becomes even worse, essentially. Essentially, we're not going to win this comparison. Why? We have been extremely successful in improving the energy efficiency of our computation units because of Moore's law. Moore's law has enabled, and Dennard scaling, they have enabled us to actually make our logic much better, but they have not helped us with memory and interconnect. As a result, we're in this bottleneck today. Okay, there are more papers you can look at. I'm not going to talk about them. But as a result, at the system level, we see the pains of this data movement overhead. More than 60% of the total system energy is spent on data movement on these applications, and many applications more than 90%. So I would argue that we do not want to move data. We actually want to rethink how we design systems to enable computation with minimal data movement, compute where it makes sense, where data resides or where it gets generated, as opposed to computing only in the compute units, today's compute units. And we want to make computing architectures much more data-centric as a result. So I'm going to specifically focus on memory and storage, but especially memory. But our argument is that you should really have computation all over the system. Essentially, a system should be a distributed system in terms of computation capability in the caches, in the main memory, in the sensors, in the storage units, in the interconnect, in the network controllers. Everywhere you should be able to do computation without having to go through a processor core. So memory is very interesting because today's memories are huge, and people have been designing applications to fit memory sizes. For example, in-memory database exists, in-memory graph processing, in-memory machine learning, in-memory media processing exists, so that we try to reduce the access to the storage units. So we're going to talk about memory. Ideally, we would like to be able to talk to memory and say, memory, could you perform this function for me, for example? Or I'm offloading this application to you, could you execute it for me? And memory does that and returns the results. Clearly, this is easier said than done. There are many, many questions over here. How do you design the compute-capable memory and the controllers? How do we design the processors and communication units? The software and hardware interface to enable this? The system software compilers and languages to make it easy? And then algorithms and theoretical foundations so that we can make the best advantage of this. Clearly, there are many, many questions over here. And it's been across the stack design. It's quite exciting. And I believe that there's a lot of work that needs to be done. I will mention the theoretical foundations over here. If you look at the theory of computation today, we've looked a lot into minimizing operations. The big O notation, big theta notation, for example, is all about operation count. It's not about data movement. And I think we really need to rethink how we theorize about computing devices going into the future, such that we have a much more data-centric theory of computation as opposed to compute-centric theory of computation. So there's a lot that we can talk about. I'm going to jump into some examples. But before that, I will mention that you can find a lot more examples on this paper that we keep updating on arXiv, if you're interested. And we have other papers also. And we also have processing in memory courses if people would like to attend and revisit what's happening currently. There's a lot more material in a full semester-long course that I can cover in this talk. So I will also argue that we need to think differently from the past approaches. But before I jump into now some examples of processing in memory, maybe I can take some questions related to what I just discussed. Any questions?
I have one question. So, do you know a paper which characterized the amount of energy consumption when you transfer data from, for instance, if we consider a genomic data center, so a paper which characterized the energy consumed by data transfer between machines, not only at at a single machine granularity scale.
Yeah. That's a great question. That's a paper that I want to also find out, but I don't know any work that has done that. Okay. Like using measurements, at least. People theorize, of course, but measurements are a hard thing to do.
Okay.
I have a question. You said that one of the reasons why we spend a lot of energy to access to memory and to moving the memory is that you have like the Mutlu, that there's a lot of operation on those memory, like prefetch, Mutlu threading, and all of this. But my question is like, is those Mutlu threading or prefetching systematically used to have access to memory or not? Because if we find a way to not use them and to directly access the memory, is it like, can we improve the efficiency of the access of memory?
Yeah, so that's a good question. Basically, can we avoid doing multi-threading and prefetching and improve efficiency that way?
Yeah.
I mean, in general, no, because these techniques are not useless. In the end, prefetching, multi-threading, caching helps. They actually help performance, and on average, they improve efficiency. But unfortunately, the cost that they add to the system is actually very high. And when they don't work, they basically degrade efficiency. So, for example, that's a very good question. Actually, we asked that question to ourselves also in a recent Micro 2022 paper in October. We presented a paper that actually received the Best Paper Award at Micro. And the idea over here was you have this complicated memory hierarchy. If you can predict if a load is going to miss the memory hierarchy, why not access the memory hierarchy, main memory directly without accessing the L1, L2, L3, L4 caches? And we designed a predictor. My student Rahul Bera is the first author. He designed a perceptron-based predictor that can accurately identify which loads will not hit in the cache hierarchy. And he showed that basically you can improve both performance and energy efficiency. So your idea is actually quite reasonable.
Wow.
Okay.
Yeah.
Nice idea.
I will refer you to that paper. It's called Fermi's.
I'm interested. Thank you.
Sure, you're welcome. Yeah. I think we need to do things like that in existing systems, but this also shows that how poorly our caches are utilized today. If you can gain significant performance by bypassing them intelligently, then that means that our caches are not working very well, including prefetches, actually, prefetches as well.
Yeah, I definitively understand your idea of putting intelligence in the architecture.
Okay, great. Thank you. Okay, now I'm moving on. Again, feel free to ask questions. Now we're going to talk about processing in memory. As I said, I think we need to think differently from the past. And we have a characterization of processing in memory. I believe there are only two approaches, but of course, if you come up with a new one, please let me know. And let me distinguish between those two approaches first. So today, processors here and memory is here. They're far away from each other. processing near memory, which is the second one over here, says processors should get closer to memory. And at some point, processing and memory should be combined in the sense that you have logic units that are inside the DRAM chips, for example, or inside the storage chips. This doesn't change the logic units as we have today. You still design some logic units, processors, CPUs, FPGAs, logic, something to do computation, basically. You just make it near and near memory. I believe this is easier to do, and this is happening in the field today. Now, what is processing using memory? Again, processor here is memory here. Forget about the processor for some time. Let's take a look at memory. Normally, we think of this as a data storage device, right? But the realization that was made, especially recently, is that this memory can also be used for computation. Basically, it has some analog computation capability that we can take advantage of, and we can use it to redesign our algorithms. And I'm going to talk about that first. So this is processing using memory exploits the analog computational capability of memory, operational principles of memory devices, so that we can do bulk data movement and computation in memory. I'm going to give you some examples. We can exploit internal connectivity to move data inside the memory chips, inside the DRAM chips specifically, but actually any kind of chip is capable of this. I will briefly mention some emerging technologies and also storage later on. And we can exploit analog computation capability. And then who knows what we can discover going into the future. I'll give you some examples. And with an example, I will start very simple. I'm going to tackle the issue of data copy and initialization. Clearly, this is important in systems. There are many, many cases where we do initialization for security, forking, for example, virtual machine cloning, and these lead to a lot of data copy. Imagine initializing a 1 terabyte database, and physically initializing it takes a lot of time. And Google, in their ISCA paper that I mentioned earlier, showed that 5% of the execution cycles across all of their workloads in their data center come from only 2 function calls, memmove and memcopy. And they actually say approaches like what I'm going to describe, citing our work, are going to be much more interesting in the future to reduce this sort of overhead. So let's take a look at how we do in-memory copy in today's systems. Basically, if you want to copy this white page to this gray page, let's say 4 kilobytes, small page, you basically have to go through the memory controller at least, but usually through the CPU if you don't do it through the direct memory access engine. Essentially, you need to move the first page byte by byte all the way into the L1, and then do the write, and then write back the data byte by byte back to memory. But why should we do that? Why not actually do this inside memory completely? Basically, the CPU tells the memory, please copy this 4 kilobyte page to another 4 kilobyte page, and don't disturb my chip, because I'm doing something else that I don't want to be bothered with this sort of copy, because you can do this alone by yourself. Right? So this is low latency, as I will show you, low bandwidth utilization on perhaps the most important system resource. You don't want to bottleneck the memory bus with copies and initialization operations that can be easily done in memory, as I will show you. No cache pollution, but you could actually eliminate that today through the direct memory access engine. No unwanted data movement on the memory bus. I will show you a mechanism that takes a 4 kilobyte page copy from 1046 nanoseconds to 90 nanoseconds unoptimized, and 3.6 microjoules to 0.04 microjoules. And the idea is very simple. If you look at DRAM, this idea works in other memory chips also, but I will give you the example of DRAM. Essentially, it consists of rows, and there's a row buffer that stores the row temporarily. This has to be there. It's in all DRAM chips. The idea is first activate the source row that you're going to copy into a destination row, which brings the data into the row buffer. Now the data is very strong in this row buffer in the sense amplifiers. And then you do another activate, which essentially connects what's in the row buffer to the destination cells. So you use row buffer as an intermediate buffer to move data from row A to row B by doing 2 consecutive activates. This requires very little logic. And in fact, as I will show you later, you can do this in almost all existing DRAM chips by violating the timing parameters. Normally, there's a timing parameter between 2 activates. You violate those 2 timing parameters, and you can do this copy reliably in almost all DRAM chips today. So negligible hardware costs. So if you want to do it really reliably, of course, you want this to be in the standard, or you want to actually design a circuit to make it completely reliable. And if you can do this, clearly the latency savings are significant, more than an order of magnitude for a 4 kilobyte page, and energy savings are even more significant. And clearly these amplify with this page size, if page size increases or copy granularity increases. I'm not going to talk about application level results because we don't have time, but you can read them in the original paper. Now, more recent work that built on our work using the soft-MC infrastructure that I described earlier showed that you can actually do row clone in existing off-the-shelf DRAM chips by violating the DRAM timing parameters. And we actually built on this work to design an end-to-end FPGA-based framework for doing processing in memory processing in DRAM, we showed that you can do row clone and also true random number generation using off-the-shelf DRAM chips. If you're interested, you can check out our prototype. I'm not going into a lot of detail. We have a paper that's coming up at TACO. It will be presented at High Peak, actually. And all of it is open source, and we're happy to support people who are interested in using it. This is, as far as we know, the first open source processing using memory prototype. It's limited, clearly, but it's usable. And we actually look at a lot of system-level issues, like memory allocation for this sort of processing using memory, how to do the alignment, etc. So there are a lot of system-level issues that you need to actually consider to make this really work. Okay, if people are interested, we're happy to use it. And at the system level, you get even more performance improvements because you eliminate a lot of the inefficiencies at the system level as well. But I will leave you to take a look at the paper for that. So there's a lot I can talk about row clone, but I will. You could actually improve this so that you could do the data copy initialization across the banks, across different subarrays, etc. But I will leave you to other works. I will mention the mindset. The mindset is memory as an accelerator. Memory is very good at doing data copy initialization, so why not offload that computation to memory? And this could be programmed similarly to a conventional accelerator as well. We're having lots of accelerators on the compute-centric side. Why not have some accelerators on the memory side as well? Okay, you can say that, okay, this was data copy and initialization. What about real computation? I want to really do multiplications, etc. Well, we can actually support the primitives to enable those. Essentially, modern DRAMs with small tweaks can support bitwise AND or NOT and majority operations at low cost by using the analog computation capability of DRAM. And the idea is to activate multiple rows, and this enables computation. I will show you in the next slide how this works in a basic manner. And this leads to 30 to 60x performance and energy improvement in these block bitwise operations, and you can read the paper for more detail. Now, this works also for emerging memory technologies, but emerging memory technologies enable even more opportunities. These are some examples. They enable, for example, because of their crossbar array structure, they enable matrix vector multiplication. And because they're non-volatile, they can operate on data with minimal movement. I will briefly mention that. I have some slides on this, but we don't have a lot of time probably, so I will not go into a lot of detail on these emerging technologies. Now let's take a look at how this works in DRAM. So you have here 3 rows, A, B, C. I'm showing only 1 cell per row and a sense amplifier and a bit line over here. Now imagine you have 8,000 of these cells concurrently in one row, and imagine 1,000 of thousands of these subarrays. So you can basically do these operations of millions of bits at the same time, and I'm showing only 1 bit. And the operation is very simple. It's called triple row activation. You concurrently activate 3 rows, meaning connect the cells to the bit line at the same time. And if you do that, based on the circuit operational principles, analog principles of the circuit, what you get is a majority function. If at least two of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end. So you can do bitwise majority across millions of cells in DRAM, assuming you have the power budget to enable this, of course. Now that's good. Now bitwise majority can be rewritten this way. If you set C to 1, you get the OR of A and B. If you set C to 0, you get the AND of A and B. Now you can do bitwise AND and bitwise OR. Now that sounds good. Unfortunately, this is still not functionally complete. To make it functionally complete, you need to have a complement or inverse operation. Now that already exists actually. If you activate 1 row, in the sense amplifiers, one side you get the state of the cell, and you get the complement of that state on the other side of the sense amplifier because of the nature of the sense amplifier. You can see that there's a cross-coupled inverter over here. Now we actually propose that you actually feed that back into the array somewhere or in some other subarray so that you can actually get the complement easily. So this NOT functionality already exists. You don't need to add any new circuitry to DRAM to do computation. You just need to enable triple row activation and with some other circuit level tricks. And we propose that in our paper. I'm not going to go into more detail. I will mention that this is functionally complete. Technically, you can actually implement any algorithm on this if you rethink your algorithm so that it's all about block bitwise operations. But of course, existing systems have some algorithms that are much more amenable to this currently. For example, database community have looked at database indices that maximize block bitwise operations, bitmaps, for example. Some database folks actually designed bit weaving engine, and they basically showed that you could do these queries much faster using block bitwise operations. Microsoft has designed a bitfunnel engine, web search engine, which is essentially doing the same thing, bitwise operations. And there are many, many other algorithms that use block bitwise operations that we have been looking at. I will mention some of them later on. Now, if you actually put this into the Mbit engine that we have discussed, you get significant performance improvements. In this particular case, we ported the bit weaving engine that was designed for databases, and we show essentially 4 to 12x performance improvement end-to-end in query latencies. And the performance improvement actually is scalable with the size of the data. As long as you remain within your memory modules, if you can parallelize the computation, this works nicely. And I'm not going into a lot more detail, a lot more other results, but the Ambit paper discusses them. If you're interested, you can take a look at it. And we've also been writing other papers that talk about this execution model, as well as the challenges in front of it. I'll mention the challenges later on in the talk. Now, more recently, we've designed what's called the SIMDRAM framework to make this more programmable and to make this more general purpose, so that the programmer specifies a desired operation. This could be any desired operation. It could be high level, it could be convolution, it could be matrix multiplication, it could be anything essentially. As long as you express it in terms of and or not logic like this, we can convert it to majority not logic. This is also called majority inverter logic. And we use some compilation methods from EPFL that essentially minimizes computation. And then we generate a sequence of DRAM commands like triple row activation, row clone, that actually execute that logic. And we associate that with a SIMDRAM instruction. This could be a matrix multiplication instruction, for example. So each instruction that's implemented in DRAM and using block bitwise operations is stored as a microprogram in the memory controller. And whenever a user application calls it, let's say matrix multiply, this gets shipped to the memory controller, and memory controller executes the microprogram that is corresponding to that particular instruction, like matrix multiplication. Right? And then the result is stored in memory. So this is the programming model. It's relatively easy to adopt, and you can actually generate a compiler for it, as we have been looking into. And the benefits of this is significant. Now you can actually implement any operation in DRAM, and you get significant performance improvements, as you can see on the slide. I'm not going to go into the details of it, but you can actually outperform GPUs as well, because GPUs have a data moment problem, and now GPUs can offload the computation to DRAM as well. And the energy efficiency also improves significantly, as you can see over here. Okay, there's more in our S+ paper from 2021. I've not gone into detail, but there's a lot more to be done in this area. In fact, there's a paper from some other group at HPCA coming up in terms of compilers for this sort of processing engine. In fact, once you start thinking of DRAM as an analog computation engine, you can do a lot more. You could do lookup table-based execution, which we discussed in this micro paper. I will not go into detail, but lookup tables enable general purpose computation functionality. These require a little bit more overhead on the DRAM side, unfortunately. So I think this is a little bit more forward-looking, but it can enable some computations that are much more difficult to do bit serially. Okay, once you have this functionality, once you have this mindset, you can actually do a lot more in DRAM. For example, we have shown that you can generate physical unclonable functions. When you reduce the latencies in DRAM, you get errors, and some of the bits become a device identifier. Some of the bits are basically, you have a unique failure pattern in the cells that can let you identify the device. And this is important for attestation, for example. And if you use processing in memory in the future, attestation and security will be important. So we need this sort of mechanisms to enable security functionality in processing in memory devices. And we've also shown that using a similar trade-off, latency reliability trade-off, you can reduce the latency. Some cells fail randomly. If you can identify those cells, these are random number generator cells, you can generate true random numbers purely inside DRAM. And you can actually use them on security critical applications that could be executed on the memory side. And more recently, we've actually found out that you can actually generate these random numbers even at higher throughput by doing what's called quadruple row activation. And these are all validated on real DRAM chips. Basically, these results are not theoretical. Real DRAM chips actually, we actually tested hundreds of DRAM chips in all of these studies, and real DRAM chips are capable of this sort of computation. But of course, once you have this sort of computation capability, you also want to design end-to-end systems to take advantage of it. And this work, Dr. Strange, as well as PyDRAM, which is an FPGA-based prototype, can actually take advantage of that end-to-end at the system level. Okay, so this was DRAM. DRAM is unique and interesting, clearly, but there's nothing special in the sense that all of the memories, I believe, are capable of this sort of analog computation. And Flash is another example. People have shown that you could actually generate true random numbers in Flash, physical unclonable functions in Flash. More recently, we've shown that in Flash, you can also do block bitwise operations using similar principles. In addition to triple row activation, you can actually increase the number of row activations. You can actually do 48 row activation, for example, in Flash, and you can do a block bitwise AND or a block bitwise OR across 48 different operands. So you can see that on Flash, you can actually gain even more benefits because you can actually compound many more bitwise AND and bitwise OR operations across large data sets. And if I don't have time to talk about it, but you can take a look at it. So this also exists in phase change memory. Other folks have been working on phase change memory, for example, or in general non-volatile memories. And the idea is very similar. Again, you can take a look at these works. Emerging memory technologies have cross-bar array operations. Very quickly, I will mention this, and then I will pause for taking questions, and then we're going to move to processing near memory. So essentially, some emerging non-volatile memory technologies enable even more opportunity. And essentially, they have cross-bar arrays, which can be used to perform dot product operations. And this is essentially Kirchhoff's laws. You can operate on multiple pieces of data using these laws. Essentially, the realization is that the bit line current is a sum of products of word line voltage times the cell conductance, which is 1 over cell's resistance. Computation is an analog domain inside the cross-bar array. But of course, this requires peripheral circuitry for digital to analog and analog to digital conversion. So this is even more forward-looking because this requires a lot of work to make it even more reliable, basically. But this is the idea. Essentially, if you look at these array, this array, a two-dimensional array, here we show two cells over here. If you look at the bit line current over here, it's a function of, it's the sum of the bit line current flowing from this cell and this cell, which is a function of the voltage that's applied to this cell times the conductance, 1 over resistance of this cell, plus the voltage applied to this cell, plus the conductance of this cell. Now, you may have a matrix of weights, and then you have an input vector. If you supply the input vector in terms of voltages, and then supply the weights, program the weights into these, let's say, resistances, you can actually do a matrix vector multiplication that way. And this is an example over here. You have the resistances and you have the voltages. This is the bit line current that has the first result, and all of the results can be computed concurrently. Okay, so I will go through this relatively quickly because I think I've harped on it, and we don't have time. And there are many papers looking at these. Are some early, relatively early papers, let's say. I believe this is very important to look at. In general, reliability issues are tough, but I believe this is why processing using memory is a little bit more forward-looking than processing near memory, because it's a computation model we have not dealt with much before. In fact, if you look at the processing in memory literature, which encompasses both, most of the literature is really about processing near memory, which we're going to talk about next. Processing using memory, exploiting this analog operational principles of memory is relatively new. The earliest papers are coming from 2015, 2014, etc. So we have stumbled upon something relatively new over here, and I believe we can perfect it over time. But this requires patience and time, clearly, and a lot of research. Now I'm going to jump to the complete different model, which is going to be easier to adopt in the near future. That's processing near memory. But before we go on to that, I would like to ask you if there are any questions in terms of what we covered so far.
Phone is typing.
Okay.
Can you read the question, or do I have to read it for you?
I cannot see it actually.
Okay. For us, have you yet found any major security concerns this introduce? Sorry.
Oh, okay. Yeah, you mean the analog
in DRAM computing?
Okay, in DRAM computing. Okay, which is processing using memory, I guess, right? So this is a good question. I think this is something that requires a lot more analysis and research, and this is something we're working on. I believe there's also people working on. If you're interested in working on it, I would suggest looking into it also. I believe issues like RowHammer get exacerbated, for example, because now you're much closer to memory and you can actually hammer multiple rows at the same time. You can do it much more quickly. So no question about that. But I believe RowHammer type of issues need to be solved with other methods also. So far, we have not found any new issues that are not known, let's say. But that doesn't mean that they don't exist. This is because there's not much work that has been in this area, been done in this area. I believe there could be new side channels, for example, that may happen because of this sort of computation. But this is something that needs to be researched. And that's a very good question.
Oops.
I have a question about like what you said earlier in the, when you said that when you have a memory and you have to copy a part of the memory elsewhere, you talk about the row buffer.
Mm-hmm.
And for me, I think that's, did you have you find the optimal size of the row buffer? Because in your example, you just take just one row, and I think it's kind of slow to copy one row after another, and so.
Oh, okay. Yeah, I think I understand your question. So this is something we cannot change, meaning DRAM designers decide the row buffer size based on the trade-offs that they have in the hardware. What we're using in this particular work is essentially taking advantage of the fact that there is a row buffer and using it for copy operations. So that's good. But I think there's a trade-off here, actually. What you're pointing out can lead to other issues, because row sizes today are quite big. You may not need to copy that huge amount of data, right, every time. This may be inefficient on its own. So can we actually somehow have more dynamically sized copy operations in DRAM supported? This is something we've been looking at. We actually have a paper on arXiv that's called Sectored DRAM. If you're interested in that, I'd recommend taking a look at it. It's called Sectored DRAM. It goes a lot into the DRAM design, which is difficult to change. But I believe there needs to be more investigation. Like, what is the right granularity? How can we support the best granularity this way?
Okay. Because I thought that the row is like kind of small.
Today it could be 4 kilobytes. It could be actually 8 kilobytes. It could be 16 kilobytes.
Okay.
Depends on the DRAM device.
Yeah.
It's not smaller than that though. No, it normally doesn't come smaller than 4 kilobytes.
Okay, it's kind of okay.
But I'm talking about a module level, of course, right? If you look at an individual chip, it's smaller actually. But normally we deal with modules in DRAM. We aggregate multiple chips together.
Thank you.
Okay, great. Very good questions. If there are no questions, then I will continue. Okay, and there will be opportunity to ask more questions. Now we're going to switch gears. We're going to look at something more familiar, in the sense that we're going to keep the computation similar, as opposed to going into analog computation capability. We're going to just look at adding more logic, but adding it near memory. And again, we're going to stick to memory as an accelerator. The question is, what kind of logic can we add to the memory side so that we can actually accelerate many important applications? This could be a CPU logic also, as we will see. Okay, so here I think looking at applications becomes very interesting, and looking at entire system designs. And that's what essentially we did when we first started looking into it in 2013 or so. We wanted to accelerate graph analytics, which is clearly important and which has a huge memory bottleneck. And this is going to become even more important. There are in-memory graph analytics frameworks. Bioinformatics is actually moving into a lot of graph-based processing. There's a lot of interesting things going on in emerging applications also. Now, if you look at graph processing, this is dominated by memory in general. You have frequent random memory accesses and little amount of computation. When you do some sort of page rank computation, for example, in this particular case, you're bound by memory. Now, it's not completely random, but there are enough random memory accesses that you're bound by memory significantly. So we asked the question, can we accelerate these graph applications significantly? And we wanted to design a system that has the basics of 3D stacked memories to begin with. So you're seeing a 3D stacked memory over here. You have a logic layer fabricated differently from the memory layers on top of it, but they're bonded together using what's called through silicon vias, meaning that you can implement any sort of computation nicely in the logic layer. And memory layers that can be specialized for memory, but they can communicate with each other at very high bandwidth, low latency, and low energy compared to existing systems. You have many through silicon vias, thousands of through silicon vias over here. And there are other true three-dimensional memory technologies that are under development today. Their multi-3D engines are examples of this. I believe this is going to be very interesting going into the future. But at the time, we wanted to look at relatively simple ones, like simple logic and many memory stacked on top of it. So we start with that. And this is going to be our basic building block. Inside the logic layer, we're going to implement processing elements. And we're going to connect many of these 3D stacked memory plus logic chips together so that we can scale the memory and computation capability. And we're going to interconnect them nicely. And we're going to design an accelerator that offloads graph computation to this distributed system of 3D stacked memory plus logic chips. And you can think of this as like a primitive GPU. You offload your graph computation on top of it. It's physically addressed. It's non-cacheable. So essentially, it's supposed to operate independently of the host processor to do a specialized computation. Now, what happens inside the logic layer? Inside the logic layer, we have simple in-order cores so that we can execute graph processing computations. They're interconnected to each other via some sort of network. And then the key technique that we use is we don't move the data, we move the computation to the data. So if you want to update a graph node, for example, the programmer is supposed to tell which function should be shipped to which node, so that you can send the function to the graph node and send the intermediate data that's needed, of course, input data, and then the computation happens in place. The update happens in place in that particular vault, particular core that houses the memory on top of it. So basically, we partition the memory across these cores, and each core has a partition of memory, and updates happen in that partition by shipping functions. So this is very similar to distributed systems programming. We program it using remote function calls, and ideally, you would like to keep the remote function calls local inside each 3D stacked memory logic chip and not communicate across these chips as much as possible. So graph partitioning becomes important, but we actually take advantage of the locality present in at least some of the application to get benefits. Okay, I'm not going to go into a lot of detail over here, but essentially you need to enable communication via the remote function calls, and we actually design a lot of prefetching mechanisms to take advantage of the vast amounts of bandwidth that we have in this system. Now, the system looks very different compared to existing systems at the time. You can see that existing systems are compute-centric. These are blue ones are the cores over here, and the rest is memory over here. And they're bottlenecked by memory. There's a dichotomy between memory and computation. And you can see that as a result, the bandwidth is very limited. Whereas if you look at what we call tesseract, computation and memory are coupled with each other. You cannot distinguish them if you look at it this way. And you can see that the amount of bandwidth that's enabled to all of these cores is 8 terabytes per second, much more significant compared to what we had at the time. And these values have scaled. Today, actually, we have a lot more, but compute-centric systems, memory bandwidth have not been scaling as much. So we actually ported a lot of applications. This requires some programming effort, clearly. It's all done in hand. And we see significant performance improvements compared to existing systems on the order of 13 to 14x, let's say, on 5 graph processing algorithms. And more recent work, this was done in 2015, more recent work improved this significantly. They basically looked at, for example, how do we handle data partitioning better? How do we improve parallelism? How do we actually do the graph partitioning better, etc.? How do we do the interrupt handling better between these cores? And they've actually shown that you can get to 100x or even more in the cumulative work. Now, we also showed that this also reduces energy significantly. At the same time, it improves performance. And more recent work showed that you can actually go to 2 orders of magnitude energy reduction. So basically, if you start going toward this direction and start specializing the system more graph applications, you can get 2 orders of magnitude improvement in performance collectively over, let's say, a decade of research, and 2 orders of magnitude energy reduction, again, collectively over decades of research. So I believe this is quite promising. And if you're interested, the paper is a whole lot more detailed than I can talk about right now. Now I will talk about more recent work that we've done, and I'm going to switch gears to storage because I believe there's some applications that are going to benefit even more if you can do in-storage computation, especially genomics, for example, because we generate a lot of data. But this is true for machine learning where there's a lot of data as well. Now let's talk about how do we do genome sequence analysis today. Basically, you may have lots of genomic data, and usually in metagenomics, for example, we have huge amounts of genomic data. We store it in the storage system, and we move it all the way through the main memory, caches, and the computation units today. And you do processing, for example, alignments, like edit distance computation. This has a lot of computation overhead and a lot of data movement overhead. Now, today's systems actually do a lot of heuristics, accelerators, and filtering to minimize the computation overhead. This makes the data movement overhead even bigger because computation overhead reduces and data movement overhead becomes a bigger fraction of the system. And clearly, there's a lot of work that has happened in main memory and caches, for example, to do computation over there. But there isn't enough work that has looked at the entire system holistically. Can we also do computation inside the storage so that we don't even move the data to main memory or caches? And that's the idea in this work. Do in-storage filtering. Filter reads that do not require further processing because they may be useless, for example, for the computation purpose that you have downstream, or they may not be good quality for future analysis. They may not be what you're interested in, basically. Quickly figure out what you're interested in the storage system and decide what to move to the, let's say, expensive parts of the system because of data movement. So we call this filtering, and there are methods to do that. This reduces the amount of data that you move to the main memory and cache and computations greatly. Of course, it depends on the use case and application, and you can read the paper for more detail. But for example, if you're interested in 2 reads that are exactly matching, and you don't need expensive computation for this, you can actually decide what is exactly matching between a genome and another genome quickly in the storage system. Non-matching reads can also be quickly figured out, actually. If two reads are very distant from each other, you can actually do a quick computation to decide that. The difficult computations, maybe you need to leave it for the computationists that are specialized for that purpose. And that's what we do, essentially. And this reduces the data moment overhead significantly. And we show that you can improve both speed up, both performance, as well as energy. The success depends on the data set properties, but you can see that it can be quite significant, like more than 1 order of magnitude in both. And again, this is not a trade-off. You improve both performance as well as energy. You don't basically have a trade-off between performance and energy. And these are techniques that we want going into the future, in my opinion. Again, I summarize this relatively quickly, but if you're interested, you can feel free to ask questions, or we can take a look at the paper.
Onur, I have a question.
Yes, please, go ahead.
So the storage device, is it a new one or?
So that's a very good question. Basically, we examine multiple different types of storage devices. It includes both new ones, like really expensive ones, as well as low-cost ones. So the benefit you get in lower-cost ones is much higher, of course. But if the storage device already has a lot of bandwidth, the benefit is lower, but we still get significant benefit in the new ones. I'll refer you to the paper for more detail.
Thank you.
Yeah, thanks. Okay, now let's move on to something else. Very quickly, I will talk about the work that I mentioned earlier. We did this work with Google a few years ago, and we wanted to analyze the effect of data movement on real workloads like this. And together, we characterized a lot of workloads. As I said, we showed that most of the system energy is spent on data movement, and we wanted to solve the problem or alleviate the problem using processing in memory, using 3D stacked memory. The challenge in these devices that are relatively small is limited area and energy budget. And we identified two second major observation. We found out that a significant fraction of the data movement often comes from very simple functions, and we can actually design specialized lightweight logic to implement these simple functions in memory. You can, of course, use a small embedded low power core, but if you actually design small fixed function accelerators, for example, for copying functions, for compression functions or decompression functions, for motion estimation and video encoding and decoding, you can actually design accelerators on the memory side. And we show that if you actually do this, you can improve both performance and energy again. Not as large as what we have shown earlier, because here we're offloading very simple functions. It's not like you're redesigning the entire application. We want it to be more, let's say, adaptable. This is function offloading. As a result, the performance and energy benefits are significant, but not as large as what I have shown you. But redesigning the application in the end leads to a lot more improvements. So I'll not talk about this in detail, but for example, in TensorFlow, you have a neural network for inference, and a lot of the inference energy is spent on data movement. And data movement often comes from two major functions for data manipulation, like packing and unpacking of data, and as well as quantization of data. And if you actually speed this up, packing and unpacking and quantization on the memory side, you get significant performance as well as energy improvements on neural network inference. And there's a lot more that I don't have time to discuss, but you can look at this paper. And again, feel free to ask questions anytime. Feel free to interrupt me. I'm not going to talk about some of the other works. There's clearly a lot of work going on in GPUs. In fact, there's a lot of work on compilers to transparently offloading things to the GPU systems, and this is one work that we have done. I will not talk about this, as I said. You can accelerate pointer chasing. This is a very latency critical workload, and if you actually offload pointer chasing in 3D stacked memory, you can gain significant performance improvements. Similarly, you can offload this completely transparently to the programmer. That's a bit tougher, a lot of work on hardware, but again, you can do that. You can actually accelerate prefetching mechanisms on the memory side. You can accelerate climate modeling. I mentioned this briefly early on. You can accelerate approximate string matching, sequence to graph mapping, and more recently, we've actually been combining multiple different stages of the genome analysis in the memory side. You can accelerate important applications like time series analysis. It's actually done a lot in electrical signals that you may collect, or any signals actually, signals from astronomy. It's used in economics, politics, etc. So I believe time series analysis is another interesting problem to look at. And more on graph pattern mining. More recently, people have been looking at graph pattern mining. Here we designed an instruction set architecture for graph mining that is amenable to processing near memory as well as processing using memory. So we actually have set-centric formulation of a lot of graph mining problems in this work. And clearly, doing bitwise operations on sets is very useful for processing in memory to take advantage of. And again, I don't have time, but this is a full system design paper that you can take a look at. And we've shown that you can actually improve database systems, hybrid transactional analytical databases significantly, and neural networks significantly. If you have time, I'm happy to talk about this neural network a little bit, and then we'll talk about adoption issues. How are we doing on time?
We can finish in 7 minutes.
Okay, okay. Maybe I'll briefly give you the idea of this neural networks, then I'll talk about adoption issues. Then we will conclude and take more questions. So very quickly, we've been working with Google on neural networks also. We wanted to do a similar study to what we did with other workloads. This is a very busy slide, but basically, we've shown that existing neural network accelerators, unfortunately, are designed monolithically. As a result, they don't handle memory accesses very well. And as a result, they operate significantly below their peak throughput and energy efficiency. This is very similar to the result that I showed you on CPUs applied to neural network accelerators. Neural network accelerators are essentially bottlenecked by data movement. And we show this in this paper. And to tackle that, we assigned a different accelerator that consists of multiple different heterogeneous accelerators. And heterogeneous accelerators, two of them are data-centric, one of them is compute-centric. And you basically offload different layers of the models to these accelerators. And this improves both performance and energy at the same time. You can see the numbers over here. It also leads to a smaller area in the end compared to a single monolithic accelerator. So I've given you the high level. You can read the paper for more details, but we've analyzed 24 edge neural network models that are used by Google. And we found out that their properties are completely different from each other, as you can see over here. We've categorized their, for example, floating point operations per byte, multiply and accumulate intensity. And you see significant differences between the layers of neural networks as well as within a layer over time. And the idea over here is, as opposed to existing HTP accelerators that are monolithic, why don't we design different sort of accelerators and have a runtime system that schedules the layers dynamically to either a compute-centric accelerator or two data-centric accelerators with specialized data flows for different layers. That's the idea. So this requires identifying layer families, which I'm not going to talk about, but you can actually find out all of this information in our paper as well as presentations. And this leads to significant energy reduction because a lot of the energy is actually spent on data access. Even more so, especially, for example, these LSTM models or transducer models, you can see that they're dominated by DRAM and off-chip interconnect. This is more than 90% in many cases. And we can reduce energy consumption by 3x on average compared to the baseline edge TPU. And also, we can improve inference throughput significantly. As I said, this also improves area efficiency, but I don't have time to talk about it. You can read our PAC paper from last year. I already talked about FPGA-based processing near memory, which is interesting, but we don't have time to go into more detail. So hopefully this gives you an idea of more data-centric system design. As I said, a lot of these require rethinking the entire stack, specializing the algorithm to the devices underneath, and also designing whatever comes in between, which I have not talked a lot about. Now I'm going to talk about that a little bit. But if you're interested, you can take a look at these papers for more detail. And we'll also talk about workload and programming issues in some of the other papers. Now I've covered these two directions. Now let me talk a little bit about adoption challenges. I think adoption is very important. And this requires a lot of rethinking across the system, because a lot of the adoption issues are related to applications, software, programming, system, security, runtime, compilation, and infrastructure to assess benefits. Clearly, there's a lot of work that needs to be done in hardware also. But in the end, hardware can be done. You can design any sort of hardware, but if the hardware doesn't get adopted by the software stack and the system stack on top of it, unfortunately, we're not going to move to fundamentally better systems. So we need a lot of research on the system side. I believe this requires a lot of change in the mindset, because there are a lot of decisions that we bake into our systems today that assume compute-centric paradigm. For example, how do we do the data mapping across devices? We basically distribute the data across memory channels today because there's a central CPU. But if you actually have a data-centric system that does processing inside the memory, the data mapping mindset needs to change. You cannot assume that there's a central CPU basically anymore. So these are some examples. I believe we need to get there, we need to revisit the entire stack in the end, but this is not going to happen overnight. We can get there step by step. So that's why we've been looking at a lot of applications. These are some things that I've covered, but some things that I have not covered also. We need to keep it simple. This is a work that I have not covered, PIM-enabled instructions. It basically pushes for simplicity. We need to solve issues like coherence. I don't have time to talk about, but coherence becomes a big bottleneck between CPU and near data processing accelerators. And there are works that are there, but there are not enough works. This is the only recent work that I'm aware of that we have done, and I have not seen a lot of work in this area. I believe there needs to be more. How to support synchronization primitives at the system level using hardware support is important. How do you support virtual memory? Unfortunately, this is a very headache type of issue, in my opinion. Virtual memory is not doing well today in existing systems because of the huge amounts of overhead that it imposes. In processing in memory, it becomes even worse. How do we tackle this virtual memory support? I believe there's a lot more, but I don't have time to cover them. But let me give you some hope. These are all research problems that we need to solve. But there's also hope because in industry, things are happening. As you can see, there are things in the processing memory landscape. I will talk about UpMem. We've been doing a lot of work together with UpMem. These folks have designed these DRAM chips that can do computation inside the bank or next to each bank. And we've been working with these systems and writing papers. You can see that there's a general purpose processor inside next to each bank. It has its own instruction memory, data memory, and DMA engine. You can see that this is actually very interesting now. And this is a near memory compute engine. You can program it relatively easily, and we talk about the programming and benchmarking of it in this paper. I will not talk about this in detail because we're almost at the end, but if you're interested, we actually talk about a lot in our talks. Juan is an expert in this topic. I don't have time to go over these key takeaways, but if you can specialize your application nicely, you can actually outperform existing CPUs and GPUs in this system. Unfortunately, not all applications can be done this way in some cases where this doesn't outperform the CPUs and GPUs. So it's a trade-off, basically. Because of the design decisions that are made in the system, you may not be able to get high performance, but so for some applications, you can get significant performance and energy improvements. Okay, if you're interested in more, you can take a look at the papers. And we have released benchmark suites openly. People can actually contribute to these benchmark suites if they're interested and read the papers. And we're happy to provide any support actually for people who are working on this topic. We've also been looking at machine learning training on this processing in memory system. If you're interested on that topic, there's more you can see. And again, you need to optimize your data representation because the computation capability of the processor that's next to the DRAM bank is not a lot. It cannot do more than 8-bit multiplication, for example. It can do some simple operations really well, but if you start doing complicated operations, it suffers. And also the frequency of that processor is not very high because it's fabricated in DRAM technology. It's 10x lower than existing systems. But even then, if you can specialize your application, use lookup tables, for example, optimize data placement and layout, you can outperform existing CPUs and GPUs. So this is actually very fascinating to me. Even though there are a lot of downsides to the existing designs of this engine, you can still outperform CPUs and GPUs if you know what you're doing and if you do it very carefully. And again, I will refer you to the papers and the talks if you're interested in this. There's also other talks. This is a very tough workload for this sort of system, sparse matrix vector multiplication. In general, sparse matrix vector multiplication tends to be a very tough workload in processing in memory systems. And we showed that in our Sigmetrics paper. Here, again, we open source a bunch of SPMV kernels. You can download it. You can improve the state of the art. And we have comprehensive analysis of sparse matrix vector multiplication that I'm not going to talk about, but you can watch Christina's talk if you're interested in this. Now, that's UpMem, which is quite interesting. That's general purpose. But some other industry has been designing special purpose engines to actually accelerate machine learning inference in particular. Samsung is one example. This is function in memory DRAM. You can see that it's 3D stacked memory. And they have actually floating point computation inside here, very different from UpMem design decisions. But it's very specialized for a very small instruction set, as you can see over here, essentially for matrix vector multiplication. And again, they've implemented the chip. It's not openly available. There are papers that they have written, as I have referenced over here. If you're interested, you can take a look at it. Samsung and Facebook together designed a thing that looks like this. It's essentially a module that consists of a bunch of DRAM chips and a buffer chip. Buffer chip does computation for recommendation inference. Again, they've seen that data moves a bottleneck, and they've written papers about it, as you can see over here. And here they aggregate the data and do recommendation inference without going into the processor. SK Hynix also designed an accelerator in memory, very similar to, at least in spirit, very similar to accelerating machine learning, but they also make different design decisions. Again, you can read about their work. These are not open source, unfortunately. UpMem is actually open. You can actually do the experiments. You have to contact these companies if you want to actually do work in this on these particular chips. Alibaba also similarly designed a DRAM die for PIM recommendation. Again, they publicly exposed this in ISSCC this year. Again, you can find more details. This is actually fascinating. I think people are now changing DRAM significantly to do processing in memory. When we first started talking about this 10 years ago, let's say, or even 15 years ago, if you push it back, nobody would touch DRAM. Basically, they would not be interested in touching DRAM. But now, as you can see, because of the issues that we've discussed, people are very interested in touching DRAM and changing it significantly to enable in-memory computation. I believe there's more to come, basically. So these are, in my opinion, this is good news, but we need to really think about, as a research community, how to enable this new technology, how to take advantage of it more, how to make it easier to program, for example, so that it can actually have substantial impact in real workloads and real systems. So for this, I think we need to develop new methodologies to understand what functions should be shipped to memory side, what functions should not be shipped to the memory side. And we've been writing papers about it too. This is very interesting. This is a study of 345 applications from many different domains. As you can see, these are really interesting domains. And we basically categorize the different functions in these domains to different bottleneck classes over here. And each class can be handled with the different data movement mitigation mechanism. For example, for the compute bound class, it makes sense to actually bring the data all the way into the caches. For DRAM bandwidth, you may actually need to ship it to memory. So you may actually need to do prefetching for some of these things, and we discuss that in the paper. And this is, again, completely open source. We invite the community to build on it. This is not completely automatic, but if someone can automate this sort of design decisions, that would be very useful for the programmers, for example. Okay, I've talked a lot about the memory-centric computing, but in the end, we want to design fundamentally energy-efficient computing architectures and fundamentally high-performance computing architectures, fundamentally sustainable architectures. I believe all of the arrows point to designing systems to be data-centric. We cannot go on with the compute-centric paradigm because data movement is really killing us, and there are a lot of issues that we have talked about. We really need to design systems where processing happens where it makes sense, as opposed to just in the processor. Okay, there's a lot more that we can talk about, but I'll leave that to other talks that you may watch. Let me conclude, and then I'm happy to stay longer and take questions. So I hope I've given you a lot of evidence that we must design systems to be balanced, high performance, energy efficient, all at the same time. This will lead us to intelligent systems. And we've focused on the data-centric principles today, but there are two major directions like data-driven and data-aware that are equally important. We should enable computation capability inside and close to memory and any type of data storage and data generation structure. This can lead to orders of magnitude improvements, as I've shown you in this talk. This can enable new application and computing platforms like a device that I can give to a doctor who can do the processing for genome analysis for a life-critical patient, for example, in minutes or even in less than a minute. It can enable a better understanding of nature, in my opinion, because we've kind of given up on existing computers to really help us understanding nature. We need to move to more computers that resemble what nature does. And I will give an example from the next slide. And who knows what else. So I believe the future is bright, but we need to do a lot of research and design across the computing stack, all levels of computer design as well as computer science, I would say. So, okay. So I think if you look at nature, and brain has been touted as one of the most impressive processing machines, let's say, it's nowhere near a compute-centric system. If you look at this, this is much more distributed. Memory and computation is not even distinguishable in some cases. And we don't quite understand, of course, currently, but it's much more data-centric. It's much more data-driven, clearly. And we believe it's much more data-aware because there's a lot of, at least evidence that shows that semantic properties of data are taken into account in the processing at different parts. If you look at languages, for example, and how they're processed, it's very heterogeneous and semantic. Again, I don't claim to understand, and in general, humanity doesn't claim to understand this machine very well. But one thing is certain: this is not compute-centric. Okay, so to get there, I believe we need to do things step by step. Okay, I'm not going to talk about these more. I will acknowledge the people who have funded us, and without their funding, this would not have been possible. And most importantly, I'll acknowledge my research group who have done essentially all the research that I've discussed. You can see some of the faces over here, and we have newsletters if you're interested in their research. Everything I've discussed, all of the papers are open source, and you can find it online. And most of the simulators, etc., are open source on our GitHub. And if you need, if you want to use any of these and need help, feel free to contact us. We're very much happy to help. And if you're interested, there's a lot more information on the special research sessions and courses we organize. We're also going to organize a tutorial at HPCA in Quebec, in Montreal, next February, I believe, on real processing and memory architecture. So if you're attending HPCA, you're welcome to come to our tutorial. As I said, we have a bunch of courses also where you can get even more up-to-date information. Processing in memory course, an example. We have genomics courses and a bunch of other courses that I'm not going to talk about, but these slides, I'm happy to make them available. Okay, this is where I'll stop. I'm happy to take more questions.
Thank you, Onur. Questions?
I think that there's a lot of things that I'm still processing, so I do not have question right now, but will contact you if I found someone after all the reflection that this conference leads.
Yeah, sure, no problem. I think people have asked a lot of good questions so far. If you have more questions, anytime you can contact me. My email's over here.
Thank you very much. Yeah.
Onur, you talked about the other real PIM technologies, so from Samsung and these other companies, and I would like to know, can we use them in a normal machine like the OpMem device?
Yeah, so that's an excellent question. Basically, OpMem device, normally you should, but they have designed the systems for it, and the system is relatively normal. But I think I would suggest talking to OpMem about it, because it depends on. So normally these are DIMMs, and these are things you should be able to plug into your machine. But there may be some power requirements, for example, depending on which type of OpMem chip is present on these modules. But technically, yes, you should be able to use it on a normal machine.
Is it the same for the other companies?
Okay, that's a great question. So that's there, I don't have enough information, but Samsung, for example, in their work, they claim that, yes, this is wherever you can plug in essentially this HBM chip, you should be able to also use it. But again, this is HBM, right? Your machine needs to support HBM2 standard for this to work. But their claim is that, yes, you can just plug in the chip and offload the computation. In fact, their claim is even stronger, I think. You don't even need to change much in your software. But again, this is not independently validated, in my opinion. I believe that's also true for SK Hynix. But again, there's even less information on that topic. And I'm not sure really about the Samsung, this AXDIM engine.
Okay. I have another question, but it's not about science. It's about where do you take time to do that? Do you have a family? Do you have?
Yeah. I mean, I think I should say the biggest credit goes to these people over here. I have a family, and they have families, a lot of them. So I think they come up with a lot of good research, and I just help them, guide them. Yeah, that's what I'd like to think. But yes, it's a lot of work, no question about that.
So, in average, how can you say about how much time you spend for a work? Let's say in average, 1 year, 2 years.
Oh, you mean for a paper, for a given paper?
Yeah, for a paper.
Oh, okay, that's a very good question. I mean, it really depends on the paper, but usually it's at least a year type of endeavor. In some cases, it's longer. For example, the RowHammer paper took much longer. It's about 2 years because we need to build the infrastructure, make it work, etc. After some point, if the infrastructure is in place and you know what you're doing, of course, it becomes easier, right? It could. The idea to paper may become, I don't know, 8 months. I'm not saying idea to publication, because publication is delayed because of the rejections, right? Clearly, rejection happens a lot for sometimes reasonable reasons, sometimes unreasonable reasons. But initial idea conception to first submission of a paper, it almost always takes a year, in my opinion, at least. If you need to build substantial infrastructure, it could be 2 years or longer.
Okay.
But I think now that the infrastructure is there for a lot of these things, if people want to get started, and if they ask for help, we can certainly help with the infrastructure. Or if people are very good at these infrastructures, they can also actually amortize the cost significantly.
Cool. Okay, no more questions.
No, I can't find one on the public chat, but yeah, some people say like thank you for
Yeah.
for this conference. It was like very open-minded.
Okay, thank you. Yes, again, as I said, feel free to contact me anytime. And if you need help with the tools that we have released, we're happy to support.
Cool.
Thank you very much.
Thank
Wow.
you very much. Thank you everyone for participating, and we great talk. Thank you.
It is a huge amount of work that you've been presenting to us, and that's a huge honor for us to having you.
Okay, thank you very much, Caroline. Thank you, Alan.
Okay, I will send you the link for the recorded video.
Okay, thank you.
Okay.
I will share my slides with you. I'll email them.
Ah,
to you.
yes.
You can
Thank you.
feel free to forward to anyone.
Goodbye.
Bye bye. Have a good evening.
How do we quit?